I am super, super pleased to welcome Dr. Lee Brown to give today's lecture. We live in the information age, and sometimes that can be overwhelming. And yet I'm always surrounded by people who are doing such amazing work, bringing that complex data to bear. And Dr. Lee is one of those people that is really good at sort of taking complex environmental issues and making them accessible. So we're so excited to have Lee not only give today's lecture, but to join the environmental studies program. She's a new lecturer in the program. So Dr. Lee's teaching and research are motivated by a desire to make a difference and to give students the tools to do so as well. And she brings really diverse teaching experiences, both in the classroom and as a research mentor. So in addition to teaching college level courses that are in the sciences and data level courses, she has taught news literacy. She's mentored countless research students. She was a woman in science mentor at the University of Georgia prior to coming to Tufts. And as teacher, she's very hands-on. She looks to sort of create problem solving with real data, and then thinking about how do you take that data and communicate it. This semester, she's teaching Intro to Environmental Fieldwork and Environmental Data Analysis and Visualization. And next year, she'll be once again teaching Intro to Environmental Fieldwork. And she's offering a really exciting new course that we want you to keep an eye out for. She's teaching ENV 127, The Art of Making an Impact in Environmental Science. Lastly, she tells me that if you're interested in doing research, sort of learning the tricks of the trade, Dr. Brown encourages you to reach out to her. Dr. Lee, thank you for joining us. I'm so excited to learn about data everywhere, dealing with the deluge to address issues of environmental concern. The screen is yours.
Thank you, Colin, for that very nice introduction, and welcome everyone. I can't see you, but I'm glad to have you here. So the title of my talk, Data Everywhere, Dealing with the Deluge to Address Issues of Environmental Concern. For the intro slide, I just made a collage, excuse me, of several images. It's just several images that I put together. But what I really like in part is this one that's in the background. This is actually from an Economist, an issue of The Economist in 2010. And I like how it just shows how there's all these data that we're pulling together and we're bombarded with, and we're trying to do our best to take some small trickle of that and pull it together to do some good for our planet and our fellow human and non-human beings. And even if it's just a trickle of that we can use to get insights to help maintain life and our limited resources. So when we think about data and how it's everywhere, we inherently really think of a term that's been ingrained in our heads in recent years, which is big data. Oops. So what are big data? What does this actually mean? Well, typically when we think about big data, we just think about the volume of the data. And this is really particularly relevant in the age of the internet and the mysterious cloud that we're told collects all this data about us from our phones and our smartwatches, among other places. And often it's scary to wonder, what's happening with those data? Where are they going? And there are 4 characteristics of big data that include volume, which is just the sheer amount of data, but also velocity, variety, veracity, and value. Volume being, yes, how much data there are, velocity being how quickly those data actually, come into servers, for instance, variety, many different types of data there are, and veracity being how reliable are these data, as well as value. And so data science and big data in large part, a lot of the conversation around this has evolved from industry, where we want to actually use data to turn data into business models that increase revenue. So thinking about turning data into money, and that's the value. But with big data in the environment, of course, that value is different. And to me, that value is turning data into insights that allow us to improve environmental outcomes of some sort, and also improve our stewardship of the earth and our relationship to it. And so these first four, the volume, velocity, variety, veracity, really refer to the data itself. And there are so many different types of data that are related to the environment. This is not even remotely exhaustive, but here in the first set of images here, there are data that are collected on the ground by field researchers. These can be both professional field researchers, that have people that have master's degrees and PhDs, and that this is their job. Also citizen scientists, which are, especially now in the big data age, science relies a huge amount on citizen scientists to collect data. And these are data that are really just collected on the ground and often can be even analyzed in the lab and then put into a form that can be uploaded in a way that other people can use them. And this refers to both current and historical records. So there are lots of data in historical records that were also collected on the ground, but that we can access. And these are particular data that are found in museums. And there is a huge volume of these data. And then there are streams of data, what we call data streams, that are uploaded in real time to various servers. And these are actually really huge in volume at the multiple terabyte level, and that are basically monitoring various things about the Earth from the ground. And then, of course, there are data that are collected in the air, remote sensing type data, or surface imagery collected by drones or satellites or even aircraft. And when we think about all these different types of data, environmental data are especially, so all of these data are characterized by volume, velocity, variety, and veracity, but environmental data especially are characterized by the huge variety and the variety of data that we actually have to pull together from many different sources and different types of data that we have to pull together to make inferences about the environment, as well as veracity. And so some of the data, like from remote sensing or from some of these Earth systems, Earth monitoring systems, we may have more faith in them because we've checked the way the data are being collected enough times. But there are sometimes when data are collected by citizen scientists, there has been debate about how reliable those data are at times. And so we really need to make sure that citizen scientists, for instance, are trained very well to collect the data, and so that we can be sure that it actually is giving us the information that is going to allow us to make reliable inferences. And then going back to value, so value really refers to the ways in which big data can be used to benefit our understanding of the environment and how we take care of it. And there are so many, again, this is not at all exhaustive, but there are tons of different ways that big data have been used, and basically models, big data have been used with models to actually provide some sort of value. And one example is using big data for species identification. So in this first image here, so a lot of wildlife data actually come from camera trap data. And these cameras collect thousands and thousands of images that for one person to go through can take a huge amount of time. But you can build models that allow you to look through these data and actually, without a human having to go through everything, which will take a huge amount of time, you can actually identify which of those slides have animals in them and what is the identity of those animals. And so you can actually put cameras out in various locations. You don't have to always have people out, which is the traditional way. People go out and they look and see what they see or how many animals they see in a certain location. But you can put these cameras out and then use models that were built for working with big data to actually identify species in these cameras. Another example that is really more relative to citizen science type data is with iNaturalist, which some of you may know is a web application for actually identifying, for uploading data about species that you see in a certain location, and then those can also be identified. So you can identify them yourself, but you can also, from from images of species that have been confirmed, you can actually, those data are actually used to confirm if what you think a species is actually what it is. And this is sort of really an ongoing process. So big data are also being used to identify bird calls from the actual call. And there was a call recently, this was actually just in June, I believe, that Google AI, which stands for Google Artificial Intelligence, and Cornell teamed up to create a Kaggle competition. Kaggle is just a platform for essentially data science projects. And they put this call out for anyone who's interested, basically anyone can do this, to work with these recordings of bird calls to create a program, to create an application that allows you to input a recording and actually know what bird it is. And the person who won this award, it actually only came out about 10 days ago, so I haven't even had a chance to look at it. But these are this is just all really an ongoing thing, what we can do with these big data. And in some ways I was surprised that we didn't already have models to actually allow us to identify birds by their call, and there are some, but obviously these are still under need of improvement, because even Cornell, which hosts the internationally known lab of ornithology, is still trying to improve these models by using more and more data that we've actually collected about these bird calls. So big data have also been used, so not just for identification, but for quantification. So in this first example, these are for remote sensing data or imagery used to actually count the number of trees in a given area. And then aerial imagery can also be used to count the number of animals within a given area. And these are all of this is done basically by feeding these data to models that actually allow you to automate this process so that humans themselves don't have to do them. And in this last case, just even something like counting the number of eggs per clutch. And a lot of these examples that I'm giving you are ecological examples, and ecology is obviously only one sort of subset of a broader environmental sciences. But because I'm an ecologist, these are where most of my examples come from. But there are obviously lots of other examples. One in particular, so big data has been used for advancing outcomes in agriculture, where we can take a lot of environmental data, and these data can be used, basically environmental data and historical crop yields, for instance, or where there might be pest outbreaks. And these are used to predict for farmers where crop yields might be highest, or where there might be, for instance, a future pest outbreak that needs to be addressed. Big data have also been used as an environmental watchdog. So Global Fishing Watch, and this is also really recent, came out with this model where essentially they're using satellite imagery and data from the tracking systems of ships to try to track the movement of ships and predict where they have been at certain times and where they will be, and also to identify from aerial imagery if that is a ship in the ocean, for instance, or if it's not, and to use that to know when these ships are actually going out of the areas in which they're supposed to be and potentially illegally fishing. And big data can also be used for environmental justice. And in this case, so I have an example here. So this is looking at census tract level data from Philadelphia, relating the percentage of children that had high blood lead levels to the median household income. And this is not something that is probably new to any of you. There's been a lot of past research and books written about the relationship between blood lead in children, for instance, and more impoverished communities. But this is an example. So big data can also just be thought of as data that are out there and are available, even if they're not always huge. So this is just Philadelphia. It's something like 367 data points. I actually pulled this together myself from blood lead level data that were available and downloading census tract data, which are big data, but to just actually create this figure that, although I expected this is what I should see, I didn't know for sure. I mean, I expected it because this is what all of the research has told us, but it's a whole different thing when you download the data and you play with it and you figure out how to put it together and you see what you've been told. And this actually can put the power into the hands of people. So how do we get there? How do we actually turn data into insight that can help us understand what's going on with the environment? So there's a role of data science in this, and data science, by definition, there are many definitions, but one definition is, I'm getting feedback. Are you, Colin?
I think you're okay. Give it a shot.
Okay. It just started. So data science, one particular definition that I like is the science of extracting meaning from complex data to support decision-making in an increasingly complex world. And data scientists are the ones who are actually expected to do this. This is, a relatively recent field that pretty much emerged post 2010. And you can see that just from this figure, and here it shows in 2010, there were really very few master's programs or other degree programs in the US dealing with data science or business analytics or data analytics. And this has grown tremendously over the past 10 years alone. And what these programs often aim to do is to give people an overarching education about all of the different aspects to doing data science. So this includes computer science expertise, math and statistics expertise, subject matter expertise. So whatever your type of data you're looking at, just understanding what those data are, learning about them. And then, some specifics of machine learning, which is the tool that's often used by data scientists to actually make predictions about what to expect given the data that we've seen so far, traditional research and traditional types of software and software development. And what it comes down to really is that if you want to do data science, you're often expected to be a unicorn. Well, I'm not a unicorn. And I don't, I think that I've done a lot of work that has fallen under the umbrella of data science. But I'm certainly not a unicorn. And I think that that's a really important thing to remember if you're working with big data or you're thinking about entering a field that you're working with big data. There's always this trade-off between knowledge depth and knowledge breadth. And you can decide really where, if you want to actually have an overarching understanding of sort of all of the broader aspects of data science versus really going into one area more deeply. And you don't have to be a unicorn unless, of course, you want to be. And while I think you should believe in yourself, for the most part, it's probably best to recognize that unicorns don't exist. And so again, there is going to be this trade-off between the depth of knowledge in any one area and expertise across many. And while there are many programs to train you in big data, I think it's good to recognize that these will often fall short in some way. And so I want to transition here slightly to telling you about a few projects that I've worked on that have required data that are bigger than the data that are traditionally collected by ecologists working on isolated projects in the field. And to clarify, when I went to grad school to get my PhD in ecology and evolution, I wanted to be that ecologist working on an isolated project in the field. And in fact, I have experience working on isolated islands, collecting data. So I actually really wanted to be that field ecologist. And although my job and my academic and professional expertise in many ways would label me as a data scientist. I didn't set out on this path intentionally, but rather really by necessity. And the necessity was the necessity of big data and actually making inferences about our world, and especially in the fields that I was interested in, which are, addressing questions related to species conservation. And so when I started out, I was really interested in understanding species responses to human disturbance. And I quickly identified birds as a model system because they're easily detected, they're well studied, they have a diverse ecology and life history, and they're also surrogates for declines in other species. And important, they have ecosystem importance and also public appeal. So if you actually want to do work that is going to enact changes in policy, for instance, the fact that a lot of people really like birds means that if your findings suggest that there are certain things that we should change about what we're doing, this will often be supported publicly, and so it will have a greater likelihood of having more of a chance of impacting policy. And so as I was reviewing what I knew about bird responses to humans, I realized that the vast majority of research to date really evaluated species responses via presence absence. So whether, in a given area, the bird species was actually there or not, or in some cases abundance. So how many of individuals of that species were in a given location. But what I realized that I was dissatisfied about was that these just occurrence data or abundance data didn't allow us to get to understand the mechanism. And so I spent the better part of a year in Central and South America, and then some more time back in the US kind of floundering, wanting to really collect data, demographic data, so data on actually how these birds were surviving and reproducing in areas with different levels of human disturbance. And I was trying to come up with a viable project, and I was going out to different locations. And so I don't know if any of you have actually worked with birds and done bird banding. You might have sort of noticed in this picture that looks like there's these little poles, but you can barely see them, and the birds are supposed to barely see them too. So I learned how to mist net birds, which is when you set up these nets that the birds don't see early in the morning, they fly into them, and you put a band on the birds. And basically these bands are used to track the birds year after year after year to ultimately estimate survival. And then you can also estimate reproduction some in various ways, but one proxy for estimating reproduction is estimating the number of juveniles to adults you have in a given year, for instance. And so I kind of knew what I needed to do to get at the mechanisms behind occurrence or abundance, and how these mechanisms were affected by human disturbance. But I started to realize that to make any real inference in population ecology, which is the field I was dipping my feet into, I would need a lot of data. And that was more than any one person could do. And I struggled and I thought of other projects, but this was really where my heart was looking across broad landscapes and trying to understand how species were responding to various types of human disturbance. And so at the time I was volunteering to collect bird banding data with this program, the Monitoring Avian Productivity and Survival program through the Institute for Bird Populations. And I was doing this, in part just to have more experience with bird banding as I was trying to do this in North America and in South America. And as I was realizing that I would really need volumes of data, and I couldn't do this even in like 3 to 4 field seasons, which would be years as a grad student, it occurred to me that if I could actually analyze these data that I was collecting with other people, so this program is actually essentially a citizen science program. So they do pay some people to collect the data at various sites across the US, but there are also volunteers that actually collect the data. And if I could analyze the data that was being collected overall, not just to the sites where I was working, then I could learn a lot more than what I could do just at a few sites on Long Island or in Central or South America or wherever I decided to work. And so I wrote to the Institute for Bird Populations. I told them what I wanted to do. They asked me to write a more specific proposal. I did, and I felt very, lucky that they actually were willing to provide me with data. So overall, they had data from 1989 and to the present, from thousands of locations and hundreds of species across the US. And I really needed to hone in on a project. So I actually just requested data for the Northeastern US. And I wanted to look at how species in the Northeastern US were impacted by human disturbance. And I was thinking of human disturbance really in terms of urbanization. So how we've changed the land. And so from this subset of the broader data they had, I basically had 20 years of data across 90 locations in the Northeastern US. And I limited this to 24 species because I had to process the data and really clean the data and make decisions. And this goes into some of the complexities of dealing with big data. Along the way, you have to really think carefully about what parts of those data you're going to use. And do you just use everything, or do you actually make specific decisions based on your domain knowledge, so your expertise about the system you're working on, or the types of models you might be using? So I knew that species that had more than 300 individuals captured, I could probably get a good estimate of survival or reproduction for those species. And then And so just to step back for a second, so some people might laugh at me that, to me, this was big data. This was the first time that I realized that of all the times that I had tried using R, for instance, if you don't know what R is, it's essentially a programming language for analyzing data and manipulating data. So I had tried using it many times previously in my graduate career and failed to read in my data, so I quit. And I realized that I needed to get past that it was going to really take me months and months of data to even begin to format the data for these species, months to run the analyses, because I was going to have to run each one species at a time. And although there were only 24, running one species at a time, formatting each of those species in Excel, and then loading it into this other point and click program that allowed me to collect survival and reproduction data was going to take me ages, and really months and months just to format the data in Excel alone. Whereas it took me a week to finally sit down and write my first R script that allowed me to batch process the records for these 24 species. And then I could rerun it from there if I added new data or found any errors, for instance. So here the real data the big data aren't big data in terms of the gigabytes of real-time data that are collected by the second from our smartphones or Apple Watches. But there were over 150,000 records. Excel couldn't even read in that much data at the time. So to me, it really was big data, and it was far bigger data than I could have collected on my own. And I had to, again, just as anyone working with big data, make really specific decisions about the data and look through it very carefully to make sure it was clean. And there were actually times that I wrote to the Institute for Bird Populations, the person that handled the data, and said, I found this thing that looks like it might be an error. Can we clarify this? So there was a lot of back and forth. So then I chose proxies for human disturbance, which I basically just looked at land cover and housing density. And I'll just show you a picture of the different bird species, because I feel like people like a little break to see pictures of animals that are cute, and especially if you like birds. Yep, so I chose the proxies for human disturbance, which were basically remote sensing data for land cover. And I also included various climate data that might also affect these demographic parameters. And in short, from this, I was actually able to make inferences about the effect of human disturbance on each of these species individually. So how some species were responding positively to human disturbance and some negatively. in their reproduction and in their survival. And then also looking at so because there were enough species that I was looking at, I could look at these species in guilds. So for instance, where they were nesting or the type of food that they ate typically, and to really understand how human disturbance was affecting these species differently. And these types of inferences that I was able to make, I wouldn't have been able to make just collecting my own data in the field as one person or even a team of 5 people. And these are the kinds of insights that we actually need to know what sort of decisions we can make for conservation. And for instance, if cavity nesters are affected, a big effort that is often made is people put out nest boxes for various species that might be cavity nesters. So the really bigger point of this is that the environment needs data science, and had the direction of the field or what I was doing, and so basically, even though I chose to be an ecologist, not a data scientist, I was essentially kind of going in that direction just by the nature of the questions that I was trying to ask. So I will transition just to an overview of another project I worked with big data. So although the previous project I was talking about used citizen science data, in part, some of the people collecting those data were actually professionals. I worked on another project here. I won't even say big data because really, if you're talking about spatio-temporal patterns, you often do need large data. And so in this project that I worked on more recently, was looking at spatio-temporal patterns of pathogen prevalence in monarch butterflies. And for this project, I worked with some collaborators, including Sonia Altizer at the University of Georgia, who runs the citizen science program that actually collects these data. So to back up for a second, monarch butterflies have a pathogen that they carry on their abdomen. It's called Ophriocistis electrosclera, or OE for short. And it basically affects their survival and their ability, especially to migrate, to do their long distance migration to Mexico, and then come back the next year to breed again and for the generations to continue. And so citizen scientists go out and collect monarchs. They put their abdomen up against a little sticky tab, and then those are sent to the University of Georgia to be screened for OE. And so here we had, we limited the data to just the northeastern US, east of the Rockies and north of about Tennessee, North Carolina, because we knew that those monarchs would actually be fully migratory. And from this, we had about 27,000 samples for over between 2006 and 2018, and nearly 500 volunteers. And some things that we actually found that we weren't expecting. So we found that, if you can see here, so lower pathogen prevalence is in more yellow, and then as you have higher pathogen prevalence, it becomes more red. So what we found that we expected was that pathogen prevalence did increase within the year as the butterflies were passing it on to each other and onto their offspring within a year. But what we might have expected from theory and disease ecology, but that we didn't expect from ahead of time, was that you kind of see these cycles where you have higher and lower prevalence, and it kind of cycles in about 3-year intervals. And an interesting thing about this too is that you see there was kind of this time where it seemed like prevalence was a little bit lower, and then in 2018 it went up again. Well, initially we only had data that we were looking at through 2017, and we said, okay, well, we know that prevalence increases within the year, and over time we see these cycles, but on average prevalence was going down. And this is with what, 12 or 13 years of data. And then when we added this extra year of data, it suddenly changes are what we were seeing, which is that, look, prevalence is going up again. So we thought that there was really a downward trend because there was a bigger period of time here where prevalence was actually decreasing, but in fact, it started to go up again. And kind of the big take home message of this is that sometimes even big data isn't really big enough. And so that's why we continue collecting data and including it in our analyses, because often that our insights will change based on this. So keeping in the theme of pathogens carried by insects, I want to transition to a project that I worked on earlier this year as a data science fellow with the Insight program that's based in Boston. And this project is actually sort of a more holistic data science project because it wasn't just having big data and analyzing it and sort of making insights, but actually using it to make real predictions about what we might expect to see. So this project that I built, it's basically, I built a web app that I called MosquitoSafe with the idea that this web app can help protect your health and the environments. So this, so MosquitoSafe is an interactive tool for advanced spatio-temporal prediction of mosquito-borne disease risk. And why is this important? Well, you can see, so this is just a map showing Eastern equine encephalitis, which I'll just refer to as EEE for short. You can see how it varies both across Massachusetts with the higher areas of risk for EEE in more warm colors and lower areas of lower risk in cooler colors. So you can see it varies both spatially and it varies temporally. And for all of these different projects I've talked to you, seems to be a theme where we have a lot of data over time and we have a lot of data over space. And questions involving spatio-temporal data or patterns are actually really inherent to a lot of environmental questions. So we can see that there's variation both across time, even within the same year, just over the course of a few months, and across space. And one thing to note is that these maps, so these maps were created by the Department of Public Health, but these data are updated by the Department of Public Health as information is received. And so there isn't really a way, I can only look at their maps and say, okay, well, if this was last year in August, this is what my risk is now, but what will my risk be in 2 months or in 3 months? I don't actually know. I can only see what's happening sort of in real time as they update the maps. And there are lots of reasons why I might want to know what my risk might be in the future. So if I want to go on vacation or something and I'm at high risk for complications, if I get a mosquito-borne disease, I actually might want to know where there is, if I'm going to be at risk or not. And there's also thinking about, so in environmental science, we often think about different stakeholders and how these questions might be of interest to them. And you can think about, so, if we want to actually spray for mosquitoes, well, we don't want to spray everywhere because we know that that's actually bad for the environment and we're not just killing mosquitoes. So we might want to actually have a way of targeting where we spray so that we're not spraying everywhere, but we can spray in areas that we know might be higher risk. And we can wait until we know that, there is an issue going on now. But often we also need to budget. We might need to budget for how high the number of cases of EEE might be in a given year. So in some years it might be low and you don't need to budget for as much spraying, but in other years it might be much higher. And so for this project, I used 16 years of mosquito trap data and testing data to assess mosquito-borne disease risk across Massachusetts. So I obtained these data from the Department of Public Health. So they essentially set up mosquito traps across 309 towns in Massachusetts. And they collect the mosquitoes 3 to 5 times per week. And then they test every individual mosquito for EEE or West Nile virus, which is WNV here. And you can just see from this figure, basically, so in the blue, there are mosquitoes that were not infected, and in the orange, they were infected. And you can see from this that there are, thousands of mosquitoes that were actually tested and thousands that were not infected, and very few that were infected. But the consequences for infected mosquitoes actually transmitting the disease to humans can be are so great that we really actually want to understand why even this small number of mosquitoes might be infected, and what things might we might be able to use to predict that. So I predicted the rate of infected mosquitoes as a function of environmental data. So I used data for all of the towns in Massachusetts, and from 2004 to 2019, which were the range of the data. And I used these climate data for all of these climate variables that I used. I created a moving average of each of those variables over 7, 14, and 21 days, which was relevant to the life cycle of the mosquito. So again, I needed to know how to find these data and analyze them, but I also needed to have some understanding, this domain knowledge of the system that I was working in, to actually make these decisions. And then I also used land cover data, and for the time being, I used 2011 because it fell kind of about in the middle of that time period. And I extracted the proportion of each of the land cover types by town for, so each of 15 different land cover types by town. Oops. Sorry for that little bar there. So, and then I used statistical multimodel inference to select the features that I used in my model to predict the prevalence of infected mosquitoes with either West Nile virus or EEE. And that's why there's ×2, because I had to build 2 models. And features in data science lingo are just the predictor variables in the model. So I use the raw land cover proportions, and then 2 other ways of compressing the raw land covered into other features that might be useful. And in the end, the raw land cover class proportions were actually the features that I used to predict whether mosquitoes were infected or not. And I used machine learning to actually optimize prediction of the proportion of mosquitoes that might be infected in any given area at any given time. And I use logistic regression and random forest classification, which are just 2 of the most basic machine learning models for classifying binary data. In this case, what it means by binary is that the mosquitoes are either infected or not infected. And then I evaluated the models using some classic approaches to evaluating the output of these machine learning models. And in the end, I found some interesting things. I found that the best predictors of West Nile virus here were also strong predictors of Eastern equine encephalitis. But the top predictors of Eastern equine encephalitis were not always the top predictors of West Nile virus. So I was able to gain some insights that might be interesting to some people. But as a true data science, I really needed to take a final step and create some sort of actionable insight from the data-driven model that was created. So in this case, I built a web app, which I'm going to pull up if I can. Let's see if I have it here. I'm going to have to change my screen sharing. Oops. So bear with me for 1 second. So if you can see this, I built this app, and basically you can enter any town in Massachusetts. So by default, I put Somerville, but you can put Arlington, for instance, and you can choose whether you want to predict the prevalence of mosquitoes that have West Nile virus or Eastern equine encephalitis. And so let's just say I choose West Nile virus, and then you select a month and a date. And obviously if I choose January, approximately 0% of mosquitoes in Arlington are going to be infected because there aren't any mosquitoes there. But if I choose something like August 1st, suddenly this number is approximately 22% of mosquitoes may be infected. And so basically, this is just a user-friendly tool that allows users to predict in any given town across Massachusetts what percentage of mosquitoes might actually be infected with either West Nile virus or EEE. And there are lots of things that I would like to do with this app still. I mean, you know, this basically, I was working on this up until right when COVID happened. And then with a 2-year-old and no daycare, it was pretty hard to work on things. And now I'm teaching 2 classes, but I would like to come back and add more to this. But this is just sort of an example of a data science project from start to finish. And so just to wrap up, I'm gonna share my screen again, my PowerPoint. Oops. So this app that I created basically allows users to predict the risk of infected mosquitoes in specific locations over time and into the future. And this also, you can actually use back of the envelope calculations to convert this into risk of actual human infection in specific locations over time. So you may not care about your risk of how many mosquitoes are infected, but you may actually care what the risk of human infection is. And this again goes back to the stakeholders idea where there are other people that might be interested in these data or this project for different reasons. So I just want to remind you all that you don't have to be a unicorn. And I'm definitely not a unicorn. I'm just learning more and more by the day. And regardless of what part of this Venn diagram we're working in, a big part of data science, both in and outside of academia, is collaboration among teams of researchers and citizen scientists and people that have expertise in a field. And this, you know, a lot of this includes, as I mentioned, citizen scientists, the work of whom whose work has actually been really instrumental to both a lot of my projects as well as other insights we've gained about the environment. And I'm also reminded, I was kind of reminded both throughout this entire semester and even as I was writing this talk, somewhat perfectly by the 2 classes I'm teaching this semester, which are data analysis and visualization and introduction to environmental fieldwork, which kind of seem like very different ends of some sort of spectrum. But in fact, they're really not. So big data is not, as much as it's often portrayed as such, it's not the end all be all. And at least in environmental fields, we really still need people on the ground and we still need people doing field work and continuing to add to the data that we have. And so regardless of where you might want to contribute, it doesn't have to be as a unicorn. So this slide is just to acknowledge some of the institutions and animals and budding scientists, because we're all really scientists, that have supported my work in the field and in front of my computer. So thank you. Sorry, that went a little over.
Thank you, Lee. That was really wonderful. And I really appreciate your call at the end to sort of keep us thinking both about data that's out there in the cloud, but data that we need to collect from the field. And you know, how long does something like your mosquito app take? I mean, that's kind of mind blowing. That's such a cool app. Could you tell us a little bit more about the app?
So
And one of the questions, just to sort of read it too, says regarding the mosquito app, 22% is a lot. At what percent would you cancel kids' soccer games? This could be useful for schools.
yeah, so I actually have another slide if this comes up, and I didn't really review the slide, but essentially 22% is a lot, but you can actually convert this into estimates of human risk by looking, you know, at the probability that any given mosquito carries infection, you know, the mosquito to human transmission rate, and then the proportion of the human population that actually exhibits symptoms, right? So a lot of us actually may have already had or been bitten by West Nile virus or EEE infected mosquitoes and nothing happened. Just like, believe it or not, a lot of us might have had Lyme disease and nothing happened. So we've had it, we've been infected with the pathogen, but nothing happened. So 22% is a lot, but there are a lot of mosquitoes, and there are a lot of mosquitoes, but we can think about kind of what's the real risk to humans. And as far as so you said something about the time it took to build an app like that. Was that kind of what you were asking, Colin?
Yes.
So
Yeah.
the great thing about this Insight program is that you don't sleep. So I think it took me about a week and a half, maybe 2 weeks. So we had 3 weeks to do that entire project. And so I don't actually recommend that people go out and use my app to make their decisions about whether or not it's safe to go somewhere. Although I mean, I built it using real data. The models came back like they were validated. But I actually there are a lot of things I would like to do with it. I mean, I only use 2 of the simplest types of machine learning models for prediction, logistic regression, and random forests, but there are a lot of other models and even newer models that have come out that I could use to actually make better predictions. And I also, I would like to actually add things like maps, like spatial maps. And there's even like, the data I had actually wanted to use, improve the model and then use it to see if I could predict what happened in 2020. And I haven't even had a chance to write the Department of Public Health guy and see if he'll share those data with me. But so in short, it can take anywhere from, 2 weeks to, in the life of scientists in academia, I don't know, 2 or 3 years. And that's just the scale. I mean, that's just the projects. So this program was really designed to help people that want to transition.
Well, it sounds like it'd be a great project for students. Leah Lubit writes, what language do you recommend people interested in data science focus on?
What language?
Yeah, so what language do you recommend people interested in data science focus on?
So I'm assuming you mean by what programming language, and the 2 that are, most commonly used are Python and R. And I suppose it depends, if you really want to work in industry, Python is kind of the star language of choice. If you're in academia, it's R. But in fact, they both have their benefits. So I would say, if you know like where you want to go, you might use that to decide. But there are actually benefits to both of them. And if you have both, you'll actually be skills in both, you'll be better off.
Yeah, thank you. Coco Gomez writes, really cool to see the whole process from field to app. Can you talk a bit about the visualization process of big data in the context of communicating important messages to the public? And also, what kind of jobs are there for students with such data skills?
So going to the last question, so what types of, so I think that the number, I mean, this is where I didn't show one of these figures, but there are figures similar to the number of increase in the number of programs that to train students in data science, that is in response to the increase in number of jobs. So there are, I think an endless number of jobs in almost any field that someone with strong data and data science skills could apply for. I do think that with all of these programs that are coming up, it is increasingly various companies, for instance, they really do want a unicorn. So 5 or 6 years ago, you could say, I'm a data scientist, and you get a job. And now the interview process is just insane. And then the first part of that question?
It was sort of like, can you talk a bit about the visualization process of big data in terms of communication?
That's a really broad question. I mean, I think, well, I mean, as with any sort of story, you want to hone your visualization to what the story is that you want to tell. And what aspects of the data that you want to highlight. I mean, in my like even just visualizations throughout the talk, I just thought about exactly what message I wanted to get across and presented the visualizations for those parts of the data. I'm not sure I'm answering the question, but it's very broad.
Well, one observation I have about your presentation was you mix it up. right? You don't have one type of graph that you always present where I feel like I'm constantly being given something new, some new way of sort of visualizing data that's really holding my attention. So I feel like part of it is there's no one way to do it. It's actually becoming, I want to say, a multi-horned sort of animal where you can think about visualization in diverse ways with each one having its own message to tell.
Yeah, that is true. And thank you. It's sometimes easier for other people to answer a question when they're not in it. And certainly there are certain types of, I mean, there are specific types of visualizations depending on the type of data you're working with. And then, you know, from those sets of visualizations, you can choose the one that seems most fitting.
So there's one last question, and what in your opinion makes a strong environmental data scientist master's program? What should I look for? Highlights, good things, red flags, as I search for grad programs to apply for this field. And if you feel like that takes a longer than an answer, your answer could be, come to my office hours. I'd love to chat with you, but go ahead and take a shot at it.
That was actually going to be my answer. come to my office hours or send me an email, because I am more than happy to talk to you. So what to look for in a program, I really think it depends on what you think you might want to do. If you really don't know what you want to do, then I would say maybe just look for a program that gives you that breadth. And as you learn more about what you really like, you will hone in on the things that parts of it you really enjoy. I mean, if I were going to go into data science now, would I do it differently than I did? I don't know. I mean, in some ways, yes, I might, take more math and statistics courses and more machine learning courses and things earlier on, and more computer science. But I chose the path I did because of my interest in ecology, and it kind of took me to where I am. And so I would want a program that allowed me to really, hone in on those areas of interest, which is kind of what I did, although it was the long route. So I think it really does depend on where your interests lie in some ways.
Well, I want to argue that taking the long route is kind of nice because it anchors you in an area that you're passionate about, and that's really important. So join me in thanking Dr. Lee Brown. Thank you, Lee, for a really wonderful talk, and I look forward to being able to be with you in person at some point in the not too distant future. Thank you so much.
Thank you, and please email me if you have questions.
And thank you all for coming.
Thank you.